Hello, everyone. Welcome to week 2 of this term in Management 56085. This week, I wanted to do a short lecture on manufacturing processes. Um, for the most part, if you work in operations, you're going to interact with manufacturing somehow. And one key thing to remember is these processes are not necessarily um, solely for manufacturing. These same kind of manufacturing processes, think of it more as production processes. So it could be applied to many different industries. So some of the learning examples or learning objectives are we want to understand what a manufacturing process is. We want to explain how manufacturing processes are organized, and we want to analyze simple manufacturing processes. So production processes, when we look at the text, um, step one is when we look at the production process, we want to source products that are the parts that are needed to make the product. In step two, we're going to make the product. And in step three, we're going to deliver a product. Now, that is simplifying this really as much as we can. Starting to look at some of the terms, lead time, that's going to be the time that's needed to respond to a customer order. In a supply chain sense, that is the amount of time it's going to take the supplier to get us our product. Customer order decoupling point, that is where inventory is positioned to allow entities in the supply chain to operate independently. Lean manufacturing is a means of achieving high levels of customer service. It's really optimizing your process to eliminate waste and improve profit, and also minimize your inventory investment. When we look at kind of the general operating philosophies in the manufacturing process, we can have make to stock, which serves customers from finished goods inventory. We can have assemble to order, which we're only going to assemble the product for the customer once they have submitted an order. So once they ask us to make it, this could be assembling components. It could be assembling pre-assembled subcomponents. It could be assembling raw materials. Make to order is going to be making the customer's product from raw materials, and engineering to order is going to be when the customer wants us to design an entire new product for them. So when we look at make to stock, examples of make to stock products, televisions, clothing, packaged food products, really anything you're going to find at the grocery store, retail, on Amazon. The essential issue here is satisfying the customers and making sure that we're balancing the level of inventory against the actual needs of the customer, make sure that we're meeting customer service expectations. This is really easy to do if you have unlimited inventory and unlimited inventory resources, but inventory costs money, and firms always want to make sure they're not tying up too much capital in the inventory area. And using lean manufacturing is going to help you achieve a higher service levels because it's going to help fine tune your inventory investment for really what you're going to do for your customer. Assemble to order. So the primary task is to define the customer order in terms of the alternative components because these are carried in our inventory. As an example, this is the way Dell makes their computers. I'm also trying to think. I think Bentley does this. When you look at the automotive industry, Ford just turns out F-150s and Explorers and Fusions. Ford says we're going to make this with these components, and we're going to make this with these features, and this and these colors, and they do it. Bentley only makes a car, or Rolls-Royce also, only makes a car when it is ordered. The order is always going to come from a dealer within their dealer network. However, that order could be the dealer ordering for stock, and there we could have the dealer, in theory, having make to stock available, or we could have a dealer that is ordering from a customer order, which at like a Bentley or a Rolls-Royce dealership, it's going to be a little bit of both. And then kind of the make to order, engineering to order can kind of blend together. Boeing's process for making commercial aircraft is a great example. The customer order to coupling point could be in either raw materials or at the manufacturing site in this process. And depending on how similar the products are, it might not even be possible to pre-order parts. It's probably very hard to pre-order a jet engine to put in your inventory from General Electric or from Pratt & Whitney or from Rolls-Royce. Anyway, just talk about Rolls-Royce's cars, but they also make a great jet engine. They have a huge plant here in Indianapolis that I'm sure ships many engines down to the Boeing facilities in St. Louis that many of our students work at. So how production processes are organized. So they can be organized by project. The product remains in a fixed location. Manufacturing equipment is moved to the product. This is similar to a construction site. Work center or job shop. So this is similar equipment or functions are grouped together. A manufacturing cell is a dedicated area where products that are similar in processing requirements are produced. This is real, I think, common in mid volumes. Assembly lines is going to be for high volumes where work progresses through the different processes, and they're arranged in progressive steps by which a product is made. Think of how Ford makes their cars. And then continuous process assembly line. This is an assembly line and it's a continuous flow. This is how you're going to make toothpaste. I think one of the fascinating places I've been is it's a Nestle factory here in Indiana where they make coffee creamer, and it's just a continual flow of coffee creamer. I would have never thought that much coffee creamer got consumed until I actually saw the amount that they put it in. I drink black coffee. That's an unrelated point, but so when we start to look at the product process framework or matrix, which is a framework that describes our strategy to how we're going to determine what our process is. So if you look at something where you look along one axis, you're going to have, is it low, one of a kind, all the way to a highly standardized commodity product. And then on the other axis, we have our volumes. Is it a low volume? Is it a high volume? So like we talked about Rolls-Royce. Rolls-Royce is going to be a low volume, but not so let's look at a house. A house is going to be low volume, low one of a kind, so that's going to be project. A Rolls-Royce is going to be low volume, but it's going to most Rolls-Royces, they're going to have a certain finite amount of variation, so it could be more of a work center. When you look at mid-volume with kind of average standardization, this could be like a jet where you could have a manufacturing cell. Then you start to look at a higher volume, a higher commoditization. That's the assembly line. That's like the Ford Explorer runs on an assembly line. And then the highly standardized, high volume product, toothpaste, lotions, ketchup, soda, that's going to be on that continuous process. So when we start to look at production system design, and we go to the project layout, this product is going to remain in a fixed location. There's a very high degree of task ordering. So thinking of task ordering is very common here. A project layout may be developed by arranging materials according to their assembly priority. So you could actually then design this project layout to where you are going and grabbing things in order according to what you're going to need. When we look at work center and we start looking at system design, the most common approach is developing this type of layout is to arrange the work centers in a way that optimizes the movement of material. We want to have optimal placement. This often means placing work centers with large interdepartmental traffic adjacent to each other. And sometimes this may be discussed or referred or known as a department, and it is focused on a particular type of operation. So if you think about when I worked at Delta Faucet Company, we had different manufacturing areas, and we would have a area that just assembled shower heads, and it was the shower head work center. And it was very well known that these departments do certain things. When we go to manufacturing cell, these are formed by allocating to similar machines to cells that are designed to work on similar products. And then the assembly line and continuous layout. I mean, this is just, they're designed for a special purpose of building a product by going through the series of progressive steps. And it is, let's make as much as we can and ideally not shut this down if we don't have to. Anyone you talk to maybe that works in automotive, you may hear that they talk about, well, if you shut down an automotive production line, it's $5,000 a minute. And when I worked for Robert Bosch Steering, we always heard that from BMW. BMW would always threaten us that if we shut down their production, we're going to have to pay $5,000 a minute. Because these continuous improvement lines or continuous assembly lines, they are designed to just constantly be working, and that overhead is assumed by the organization that it's always running. So when you start to look at you're investing in the development of a product, in the development of an assembly line, what is the break-even analysis? Will this pay for itself? This is a very standard accounting principle. I'm sure most of you worked with it, but it's defined as a very standard approach. Different organizations may have slight different flavors, slight different variables that they're putting into this. And this model is really seeking to determine the point in units produced where the company will start making a profit on the process. And that helps it also figure out your ROI. And then the model seeks to determine the points or where it's equal. So once it's equal, after that equal point, then you're going to start making a profit. And the formula for this, for the break-even demand, is you're going to take the purchase cost or process or equipment, and you're going to divide that by the price per unit minus the cost per unit. Or you could also take total fixed costs of process or equipment and divide it by unit price to customer minus the variable cost per unit. And this is in the text. I believe that's 7. Maybe it's figure 7.13. So if we look at an example of a break-even analysis, let's say we buy something for $20. We could buy it externally for $20. We could make it on a lathe for $75. We could make it on a machining center for $15. Buying it has no fixed cost. The lathe has $80,000 in fixed cost, and a machining center has $20,000 in fixed cost. So, a lathe is a very simple piece of manufacturing equipment. It does not work as fast as a machining center, and there's a little more interaction from the operator to make this go. The machining center, however, there's typically, if you have a machining center, these are often called CNC machines or Swiss machines, or hydromats sometimes. They're more continuous running machining centers, and you could have one operator, maybe run 2 or 3 of them at the same time, maybe 4 if they're a good operator. Whereas a lathe, you're going to have one dedicated person on a lathe. So when you start to look at this, if you purchase it, it's simply $200 times the demand. However, if you're going to use a lathe, it is $80,000 for the lathe plus $75 times your demand. And then if you're going to produce using a machining center, it's going to be that $200,000 plus the 15 times the demand. So really, when you look at this, it all depends, and this helps really illustrate with your where your volume comes into play. So if it's a very low volume, you probably want to purchase it. If it's a mid volume, you probably want to use a lathe. If it's a high volume, you want to buy the machining center. However, if it's a low volume, but you do see it ramping up significantly, maybe you go ahead and invest in the machining center. I mean, that's a business situation that you have to talk with a business about. So, and as you look at this, as your volume increases, the cost to buy, it's always going to be kind of that same $200 a unit, and it's going to be a very stable trajectory. However, your cost to make on a semi-automatic lathe is going to start out lower. So the cost to make it on a semi-automatic lathe is going to start out higher than it is going to start out than you're buying, and eventually there's going to be a break-even point, and then all of a sudden it's going to be the best option. Making on a machining center is going to start out as your highest option, and as you see your volumes increase, it's going to become your lowest cost option. So there is a chart in the book. Example 7.1 is a really good chart. So let's say we're looking at different demand points, and I think at a demand of 2,000, um, that's going to be point A on that chart. Demand of 2,000. It's going to show our break even point for that. So 2,000 is going to be the break even point of where it makes sense to make it on a lathe. So when we start to look at manufacturing process flow and design, manufacturing process flow design it's going to be a method of, this is how we evaluate the specific processes that material follows as they move through your plant. And this is going to be from when it comes in the door off of the truck from your supplier to when it goes out the door to your customer. It's going to, and it may leave to go have secondary processes taken care of on it. And this is often going to be called WIP, work in progress. So this manufacturing process flow design is how you manage your WIP. The focus should be on identification of activities that can be minimized or eliminated. So when you really want to optimize your manufacturing process, where are the bottlenecks? How can we eliminate that bottleneck? How can we improve that bottleneck? We want to look at our movements. We want to look at our storage. Every time we touch it, every time something happens to it, the fewer the moves, we're going to have less delays. Can we minimize our storage, minimize the square footage we need to store it? And how can we make this flow better throughout our plant? So when you're working with your department that's going to really work to identify what is your manufacturing process flow, how do we design the manufacturing process flow? Really, it's going to start with the assembly drawing. So how is this part made? What are the steps to make it? And then after you have that assembly drawing, and that's an exploded view of the product showing the component parts, then we do an assembly chart, and this shows how they're going together, when they happen, how they happen, what types of equipment, what types of people you need to make it happen. What is the and then we have an operation routing sheet. So once we know that, we can then start to specify the operations, what steps are taking place and how they're routed, and start to have a map of how this walks through our plant. And then once we have that, we can put together a flow chart. And this is going to denote what happens to the product as it progresses. So we know that it goes from the warehouse to cutting, to bending, to welding, to painting, to screwing, to packaging. Well, then that process flow chart is actually going to go into detail of what happens and how we do each step. So I think if you were curious a little bit more about this, I would definitely look at. I think the name of the company is Boothright Doyhurst. I've always mispronounced their last name. I'll try to find it and post it in the announcement. So it's a company out of Rhode Island, and they have a software designed for manufacturing and assembly, and is an absolute fantastic software. And it really helps you understand how can you optimize your design to remove cost and delay out of your manufacturing process. So when we start to think about this, we really got to look at all the different components that go into the manufacturing, and we start to draw out the maps. We look at a sample assembly chart, and we put, so we may do when do we insert a new part? When do we rivet it? When do we bolt it? When do we fasten it? When do we package it? And really, you want to be able to take stock in every step of the process to make sure that you are not underestimating your fixed or variable cost. Because if you do this wrong, it's really paramount to know that if you miscalculate, you could assume you're making a product for $10 and assume you have some other fixed overhead cost, and makes it $15 in total cost. You sell it for 20 and you think you're making a profit. Well, if you miss 3 or 4 steps and maybe your cost to make it is 15, and then you have an additional $5 and your cost is 20 and you're selling it for 20, and you're doing all that to make no money. So then all of that effort is really for naught for your organization. So it's really important to consider when you're looking at your manufacturing processes to make sure that you're working with everyone in your organization. You're really aligning and making sure that everything you do is accounted for. Um, you don't want to overestimate, because if you overestimate, then you're not competitive in the market. And if you underestimate, you could run the risk of not making money, or worse yet, losing money. So it's very important that you have a cross-functional organization that sets these up, that reviews them, audits them, and really provides that final stamp when you're calculating your price. So that was really just kind of a high-level look at, I believe it's going to be chapter 7 in your text on the manufacturing processes. So I hope everyone took something from that. If you have any questions, if you want to talk about this kind of just as a more casual conversation, if you want to learn more about DFMA, I'm always excited to talk about it. If you want to even speak with someone that does it for a living, I can connect you with some of my former colleagues. So thank you, everyone. Have a great day.